So I've basically given you a brief overview of the horizontal grade that often modelers have to be concerned about. And then they also have to be concerned about the vertical grade, and there are different ways they do that, the different ways that you can do that. One of them is called the Z-coordinate system, where in the vertical direction you basically take a series of depth levels. Okay, I mean it is much easier to set up. You know, you can change the depth of each. I mean the height of each level if you want. Locally you can do that, but it's easier to set up, and it's called the Z level. And there is the terrain following coordinate system that modelers often use, and this is set up to often mimic the bathymetry, right? So that near the ocean bottom, where you have all these bumps and so on, it's better to have, you know, a terrain following coordinate system so that things run smoothly, okay, with the bathymetry. So some models are basically set up to use this so-called terrain following approach. Then there is the density coordinate system as well. In the deep ocean, I mean the layers are basically layers of different densities. Okay, so this is often set up to be used mostly at depth. Okay, in the deep ocean where there's less mixing going on. It doesn't work so well in poor regions with high vertical mixing that is going. And so that is one of the things you will notice or you will come across when you are doing ocean modeling, that some models use a so-called density coordinate model. So there are these three different ways you can do that. Of course, you can try to take advantage of all these three and come out with what is called a hybrid coordinate, which uses all these three different ones, and it applies the best suited coordinate system in different regions of the ocean. Okay, so in the surface, for instance, it could use the Z coordinate. Deep down, it uses the density coordinate, and then when you go down, you use the terrain following coordinate to follow the terrain or the bathymetry. Of course, it is very advantageous, but it comes with a high computational cost. And the HICOM model, for instance, uses the hybrid coordinate model. That is why it's called HICOM. It's hybrid coordinates ocean model. Okay. So that is about the vertical coordinates. So remember, we said when you're modeling after discretization, you also have to think about horizontal coordinates, think about vertical coordinates, and then you have to think about the boundary conditions. Okay, so there are conditions at the surface, there are winds, there are exchange of fluxes at the surface, which you have to be concerned about. At the bottom of the ocean, you have to be concerned about the topography or the bathymetry that you use. Okay, that is why hydrography is very important. You need the bathymetric information to be accurate in order to have accurate data. Velocity normal to the bottom, for instance, should be 0. You could have lateral boundary conditions that are open or closed. So you have to take that into account. And flow normal to a solid boundary wall is 0, for instance. So these are some boundary conditions that often you have to be concerned about, or modelers are often concerned about. Okay, so here's a summary of the process. You have a complex system of differential equations that are nonlinear. These are often converted into a set of algebraic equations, and then you go through a step-by-step process or method of solution. Okay, you step through it, and then at selected point in space. All right, that gives you the model spatial grid. So most often, and then of course you have to be concerned about the boundary conditions, what is happening at the surface, and then at the bottom, what is happening within the ocean itself. Okay, and it takes years to come up with a good ocean model, several years with several scientists and collaborators to actually develop a good model. And so one way to go about modeling is to develop your own model from the equations. Another is, there are several very good models that have already been developed and in existence. You can take them, study them, and then use them. Okay, so that is probably one of the ways I will advise that you go for now. So one of the models is the MIT GCM. So right now I'm just exposing you to some of the models that are available that you can try. Go to the website. There is documentation on these models. There is example cases that will show you how you set them up. I'll talk a bit about that later on. But the MIT GCM is the general MIT general circulation model that you can look at. There is the ROMS model. It's called the Regional Ocean Modeling System. It also has a good following and good help. Okay, so it is the original model that you can also use. There is HICOM as well. I will advise that you probably look at MIT GCM and ROMS first before going into HICOM, which is a little more complex than the first two. Okay, so these are some existing ocean models that you can take a look at. So now I'll just talk a bit about some simple cases, test cases. For instance, if you try using some of these models, they have some cases that you can often use to help you set up the model and learn how to use it and all of that. So this is just an example of that. So the Upwelling case is a typical case, a classical one for the ROMS modeling. All right. So here you have a domain that is set up. It is stratified. There's lighter fluid and then heavier and colder fluid below, and then you have wind that is blowing from east to west. Okay, at 0.1 pascals. Okay, so wind is blowing this way. Because the wind is blowing, it's sort of pushing the fluid. By so doing, the fluid below wants to upwell, wants to come up to the surface. And of course, upwelling is important for fisheries and all of that. Okay, so we're just talking about the physics right now. Okay, so here that's a setup. Just to show you a simple case. So this is what I was describing. So this is the depth of the domain. There's wind blowing from east to west. It's going blowing that way. Because the wind is blowing that way, pushes this fluid, and the fluid below wants to upwell. So when you set up ROMS on your laptop, your computer, and test it, you often test it with this upwelling case. All right, and when it's done right, you should be able to plot the data and have this show up. So because the wind is blowing, the heavier fluid below begins to move up and begins to so-called upwell. Okay, again, this is just a simple test case to help you know that yes, you have set up your model correctly. So you have initially everything is uniform, nice, and then once the wind is blowing, the fluid below begins to move upward or upwell. Okay, so that is the upwelling case. You can also try to set up a little more interesting and a little more complex, interesting case where you set up a real regional domain, okay, and do some kind of a real regional modeling. So this is just a small domain around the Gulf of Guinea, all right, where Ghana is around there, Nigeria probably there, and so on. So this is the Gulf of Guinea, so you can set up this. So I set this up on ROMS as well. And these are some of the operational guidelines that you often go through step-by-step process before you actually come up with results. So you often have to choose a domain and a resolution, and then once you do that, you build a bathymetry, all right? And then you have to interpolate atmospheric forcing if you want the winds to be part of your process. You interpolate the wind forcing which you get from somewhere into your domain. And then you have to choose a vertical structure. You can use the Z coordinate, the terrain following and all of that. Then you interpolate the temperature and salinity from climatology. You also get this data from a repository somewhere. And then interpolate to your domain. And then you run your simulations based on the setup, what you want to see, and then you analyze your results. So this is often some of the guidelines you go through. So once you have done this, then you analyze your results, and I'll show you some of this